This is CPE 133. This is the chapter regarding muxes from free-range Verilog Foundation modeling. This is roughly chapter 8. This is part B of chapter 8. We want to start talking about generic modeling. Here's that disclaimer again. Once again, another lecture on Verilog. You actually need to sit down and start coding and debugging, etc. to actually learn this. You're not going to learn it from a video or reading about it in a textbook. So generic modeling in Verilog is super important. It allows you to create really efficient models and also allows you to create your circuits really in an efficient manner. So this essentially it supports code reuse, which is essentially modularity regarding digital circuits, but it also promotes just generic modeling. So Verilog has a bunch of different supporting mechanisms for generic modeling, and we're essentially going to mess with two of them, which is code reuse and generic modeling. And so the code reuse is kind of the structural modeling concept, but the generic modeling is, I call them parameterized models. So it's relatively simple to do. There is some syntax you need to get used to, so it's not a big deal. Once you get used to that syntax, it's just becomes second nature. Now the issue here is that my design requires a whole bunch of different 2-to-1 muxes, blah blah blah. Well, I'm not going to redefine a 2-to-1 mux every time I need it. It's particularly if the 2-to-1 mux has different data widths, and so the data widths are different. I need a generic way of not only using a 2-to-1 mux, which is instantiation, but also changing the data width when I instantiate it, and that's what we're going to talk about today. We're going to use these parameter constructs. There's actually two types. There's module parameters and specify parameters. We're only going to use the module parameters. And what it's going to allow us to do is that when we specify a module, it's going to, when we instantiate a module, it's going to allow us to choose some variable part of that module. In particular, what it's going to allow us to do is to choose the width of the inputs and outputs. So I know there's a bunch of different ways to do this. I've actually landed on one way, and I use that way all the time. It works quite well particularly without obnoxious warnings by the synthesizer. So this is our model for a parameterized circuit. And it's wrong, of course. Gotta go fix that. So anyway, so this is a 4-to-1 mux. We've seen this before, but what we're doing here is not specifying the data width. We're going to keep that generic, and we're going to write the model such that it is generic. So here's the model. It happens to be implemented with a case statement. I don't want to... Here is the solution for this problem, and once again, get that fixed there. This represents implementation using a case statement. That's just completely arbitrary. Now, the issue here is that the data width is going to be variable, and what we need to do is specify that when we instantiate the module. But this is the definition. This is an instantiation. So what we do here is we use this parameter. We define this parameter n, and we assign it to 8. So the parameter itself is n, and you can see n is used in the data widths of these declarations here. So n is variable, it can be assigned to anything. So the issue is when I assign it this way, what happens is it defaults to 8 bits. But when I instantiate it, I can actually change that n to anything I want. And you'll see that later. If I don't change it, if I don't respecify the parameter, it defaults to 8, but I can respecify it to anything I want. So it's really the same mux, but the data widths are different. And instead of knowing in advance exactly what they are, I'm going to use a variable, which is the parameter. And so other than that, this part of the code looks exactly the same. I have used the star operator, which essentially is a shorthand notation way of saying that this always block here is sensitive to all the module's inputs, which are the select and data inputs. Do notice that the couple things here, the input width of the data matches the output width of the data, and the output is declared as a reg type because I'm assigning that from within a procedural block, which is the always block. So that's pretty straightforward. Like I said, it's very much like the non-generic solution, but let's look at the important part here is how I instantiate this thing. So here's my code from before, and this is how I'm going to instantiate it. Typically speaking, I put an instantiation template up in the comments of these modules, such that I can just cut and paste these things. So this happens to be what I'm going to do is take this module here and instantiate it as a 16-bit 4-to-1 mux. Okay, so check this out. This name matches this name here, but what I'm going to do here in the instantiation is override this parameter. It's at 8. I'm overriding it to be 16, so that means the data inputs and outputs on this mux are now 16 bits wide. So I've left these X's in here just as an ugly place marker to remind myself that I've got to go replace these things. I got to replace all the inputs and the outputs with actual values from my top level circuit. So once again, this is the definition of a generic n-bit 4-to-1 mux. This is the instantiation template that I will use to instantiate a 16-bit 4-to-1 mux. So for lack of a better place to put it in here, there's particularly things, we're making generic designs and generic modules, and sometimes what you'll see is that there are inputs and outputs on the modules that you either don't use or don't care about. Essentially, the inputs you don't use, the outputs you don't care about. And so there's a really specific rule to do this. Never modify the instantiation template, certainly never modify the model. The idea here is, which is these two items right here. The idea here is when you map it, every input needs a value, so you have to provide it with every input with a value. Typically you provide it with a value that if you're not using it, that doesn't affect your circuit. So you turn the clear off, etc., etc. Also, on the outputs, you leave the associated parentheses blank, which is these parentheses right here. So if I wasn't using the output, I would just leave a blank parentheses like that. But never, like I said, never chop the data out of your circuit. Chop the unused stuff out of your circuit or out of your instantiation template. So that's it. In summary here, we're talking about the muxes, which are foundation modules. It's a classic selection circuit in digital design. Now these circuits are not overly complicated theoretically, but to implement them they get kind of complicated and long, which is why we choose to use behavioral modeling. It makes it pretty easy. Additionally, what we are looking at here is a generic modeling, and we've had a form of genericity in that we had structural modeling, but now we've got into this parameter values, which allows me to change certain circuit data widths when I instantiate the circuit. Additionally, when I'm instantiating modules, I have to make sure that I assign every input, and even if I use it or not. So if I don't use it, I still have to assign a value on the inputs. Unused outputs, typically I'm just going to leave the parentheses blank. I'm going to leave the signal in the instantiation template. And why this is important is because unused inputs start coming up quite a bit when you start using parameterized models and start reusing your code.